C. Davis, talking about MCore, a new approach to numerical modeling of the atmosphere.
Hello? Hello? All right. Good morning, everybody. My name is Paul Ulrich, formerly of University of Michigan, as of September 1st, as of University of California, Davis. I'd like to warn you in advance, I made a valiant effort yesterday in order to try to cut down the number of slides in my presentation. So I started yesterday with 40 slides, and after 3 hours of hard labor, ended up with 41 slides. So, for what it's worth, I will try to go through things quickly, but as Jean Coté said yesterday, do not let your speaker get away with anything, and make sure that you are very thorough at asking questions. So the outline of this talk, I'm going to talk about MCore, its updates and directions, where we've gone since last time I talked about this. I'm going to talk about semi-Lagrangian finite volume advection, and I'm going to talk about Ader finite volume methods, and then do a summary and future work. So technically, this talk could fit into the dynamic core section. It can fit into the advection section, or it can fit into the time-stepping section. I figured I may as well just throw everything together. So talking about MCore, for those of you who have heard of MCore, the basic mission statement / goal that we're aiming for here is to develop a non-hydrostatic atmosphere model which is high-order accurate, scalable on parallel hardware, and is amenable to the use of adaptive meshes in order to enhance regions of interest. So our eventual goal for this is to do basically regional climate modeling over an area such as California in order to determine how precipitation is changing in time. And for that, we're going to be wanting all of these features. The construction of the model, as it stands right now, it's a global atmospheric modeling environment built using a finite volume approach consisting of the following components. It's built on a cube sphere grid in order to ensure the parallel scalability and not deal with the pole problem. It has a cubic subgrid scale reconstruction, so we're aiming for 4th order accuracy in our methods. We are using the Awesome Plus Up low-speed Riemann solver, which was designed in 2006. It's a great Riemann solver for low-speed problems, such as those in atmospheric flows. We use high-order flux recovery in order to ensure that 4th order accuracy. We use Runge-Kutta-Rosenbrock dimension splitting, which means we basically have a fully implicit vertical coupled with a fully explicit horizontal, using a high-order coupling. And we use 4th order advection with flux-corrected transport in order to ensure positivity and monotonicity of the scheme. So with finite volume methods, just to review briefly, state variables are stored, in this case density, momentum, and energy are stored as element averaged quantities over each cell on the grid. Finite volume methods do not possess or do not suffer from spectral ringing, which is very common in spectral transform method, or possess irregular computational modes, which may be present in a non-uniformly spaced method. Finite volume methods can be easily made to satisfy monotonicity and positivity constraints. As I mentioned, flux-corrected transport works pretty much directly on these methods, or slope limiting has been around since the 1970s, and whatnot. So they're very robust techniques. They've been used in a variety of fields. High-order techniques can hide grid imprinting as well due to the cube sphere geometry. So with any regular grid, inevitably you're dealing with a grid imprinting issue, which you want to avoid. If you're on an icosahedral grid, you typically enhance wave number 5. On a cube sphere grid, you enhance wave number 4. You want to ensure that that artificial forcing is as small as possible. So the cube sphere grid looks like this. Basically, it's like taking a cubic balloon, placing it inside of a sphere, and inflating that balloon so that it fills the whole volume of the sphere. There are several desirable properties. For instance, no polar singularities, which you would expect from the regular latitude-longitude mesh. The grid faces are individually regular, so whatever Cartesian method you have that works on a Cartesian quadrilateral mesh, very easy to apply in this case, also very easy to store in memory. Some difficulty at panel edges because you have 2 coordinate systems intersecting at that point, which are non-orthogonal to one another. So that needs to be dealt with. But we have methods around that. In terms of multi-resolution support, there's various approaches we can use. Todd, for instance, earlier showed the MPAS ocean model, which uses a icosahedral grid, which is slowly stretched in order to obtain higher resolution over a small region of the domain. And that's one method in order to obtain higher resolution in a particular region. In our case, we're using a non-conformal grid setup based on the Chombo approach that Phil talked about earlier. Basically, we use mesh cells which are instantaneously refined over a particular mesh resolution interface, and consequently, we can stack our cells as desired. So one advantage of this approach is the fact that it's more amenable to adaptive mesh refinement. So if you need to change the grid partway through the simulation, it's very easy to chop up grid cells into smaller values or take finer grid cells and coarsen them. So one thing people ask is why are we using high order accuracy? And the reason for this is very closely related to the presence of mesh refinement and the fact that we're on an A grid. So if you have a coarse grid on the left and a fine grid on the right, it's generally the case that in the presence of mesh refinement, numerical methods will lose one order of accuracy. This is essentially due to symmetry breaking. Phil talked about this again briefly earlier this week. If we start with a linear approach, our second order method, if we have a mesh refinement interface, then we're dropping down to first order accuracy, and that's somewhat disastrous, especially given what I show in this, which is the maximum resolved wavelength of a given wave given an order of accuracy of the corresponding scheme. What this essentially says is this is the shortest wave up here that can be represented on the grid in terms of delta x spacing with a 0.1% error in the dispersion relationship. So that ensures that your phase errors are not too large and your damping associated with the method is not too large. It turns out that for most first order methods, you're really only resolving waves at the 70 delta x scale. So you're basically throwing away a ton of computing power here because anything smaller than 70 delta x is not being resolved with any sufficient level of accuracy. At second order, we do significantly better. Discontinuous Galerkin, for some reason, does very well, and staggered finite difference, which is very popular in the community, is also significantly better than the other methods. And as we go to higher order accuracy, we eventually get convergence, or near convergence, and a very slow decay after about third order accuracy to about 6 delta x or so. So we're aiming for fourth order methods. So if we lose an order of accuracy, then we're in the third order regime and still not doing too bad. So the conservative formulation we'll be solving looks like this. We have density, momentum, potential temperature, and these are evolved in a finite volume type approach. Subgrid scale reconstruction in the finite volume approach. State variables are stored as element average values on the A grid. In our case, the A grid is a preferred choice for non-conformal variable resolution modeling since the staggered grid has issues with wave reflection at sudden refinement boundaries. So for instance, see my paper with Christian Jablanowski in 2011. There's another paper by David Long and John Thuburn that talked about this as well. So we have state variables that are element averages. Since we're a finite volume method, every cell only has 1 degree of freedom. So in order to actually get an order of accuracy higher than 1, you need to use neighboring values to build a subgrid scale reconstruction. We're going to use a cubic reconstruction, which is fourth order accurate, and that fits through 5 cells as best as it can and provides fourth order subgrid scale accuracy within a given cell. In 2D, we use a diamond-shaped stencil, which is 5 by 5, but we don't use these corner points here to provide fourth order accuracy without any sort of dimension splitting in the scheme. So using that technique, we use our element average values, and we can obtain some semblance of understanding of how the subgrid scale behaves in that case. Using the subgrid scale, then, we use that in order to compute source terms over the cell that take into account variations of the subgrid scale within the cell, as well as computing fluxes along the edges, taking into account the fact that the flux varies. So for a typical finite volume approach, we have a conservation law that looks like this. We integrate over an element and apply the divergence theorem. So we get a time evolution of the element average state, which is known within every cell, as a function of the flux through the element boundary and element average source terms present in the equations. So using the conservative form of the Euler equations I showed you earlier. In order to obtain high order accuracy along edges, this is a very important concept. We use Bird and Colella 2005 convolution. So we sample our subgrid scale reconstruction within every cell. Remember, every cell has a different subgrid scale reconstruction associated with it. We sample that at the middle of every edge. And we need to know these 3 sample values at one edge and its 2 immediately adjacent neighbors. The flux that we require is the flux across this edge. If you were to simply calculate the flux at this point and then multiply it by the length of the edge, you get a second order flux, and your scheme is going to be second order accurate. Since we're aiming for fourth order accuracy, we need to do slightly better. So step one, compute the edge-centered components of the flux vector across that edge using the known subgrid scale reconstructions. We compute point-wise fluxes at these points and fit a parabola through the three point-wise flux values. So you basically get a parabola along this green line here through those 3 points. And then we integrate that parabola over the red region here. That gives us a fourth order approximation to the flux. You might be wondering, but it's only a quadratic that we're integrating, but we're doing it symmetrically, so you get fourth order accuracy out of it for free. Okay, so using our method, we ran a bunch of test cases, especially at DCMIP back at the end of July. And one of the test cases is mountain waves over a small planet. This is a non-hydrostatic test case. We reduced the irradius of the Earth 500 times and put in a Shar mountain with a constant background flow, and consequently we got a non-hydrostatic wave response associated with the presence of the mountain. There's a damping layer up there, so don't think that that's anything physically relevant. But this is the whole domain that we're plotting. We ran the domain up to 30 kilometers and ran the wave out for 2 hours, which allows the wave to actually go around the planet roughly twice. So you'll notice the wave goes out one side of the domain and comes back in the other side and starts interfering with itself, and you get cool checkerboarding type effects there. Comparing our model against other popular atmospheric models, I really like this plot because MCore looks very good here. The GFGL finite volume cubed model is another cube sphere model, similarly finite volume approach. It has wave number 4 grid imprinting here. The spectral element model has clear spectral ringing associated with it that's not present in MCore. And home, if you choose your contour lines appropriately, you get a little bit of spectral ringing too, but that's how it goes. All right, so that's basically what's been going on with MCore so far. It'll be hopefully integrated into Chombo, and then we'll get adaptive mesh refinement working, and then that'll be very exciting, and we'll be able to do some science. So I'm going to talk about 2 experimental concepts related to basically things that have been talked about previously here. The first one is basically improvements to both these are basically improvements to MCore that we're trying out using numerical techniques which have been developed in other fields or which have been developed particularly for this model. And so hopefully it might lend some inspiration to your own work. Or you might come back and be like, no, that's a horrible idea. Don't try that. All right, so as we know, advection is a very, very important component of any atmospheric model. If you have 110 tracer species, advection is going to take a huge quantity of time. More than likely the dominant amount of time of the computational speed on your computer. So you want to make sure that advection is done as efficiently as possible, but you also need to maintain a lot of accurate and desirable features that the chemistry people are going to want whenever they're implementing physical parameterizations and whatnot based on these advected values. So the Lagrangian frame is kind of the natural way to think about the advection equation, but in practice this is really difficult to do. Apologies to Pete Bossler, who presented about Lagrangian schemes earlier. I warned him in advance I'd say this. So this method tends to parallelize poorly because you're not sure how much of your element is on which processor, if the dynamics is being run on an Eulerian grid and the advection is on a Lagrangian grid, then it gets very confusing. So in general, this is difficult to implement in practice. So usually what we do then is use semi-Lagrangian finite volume techniques. Under this approach, Lagrangian methods are the natural approach for advection, but can lead to strong deformation and do not parallelize well. Point-wise semi-Lagrangian methods have known issues with conservation of tracer mass, so if you just transport around a bunch of point values, often the remapping doesn't work properly, and then you need to implement a mass fixer in order to ensure that you're actually conserving tracer mass. There are more recently developed approaches which avoid this, which are also semi-Lagrangian. For instance, upstream integrated semi-Lagrangian methods, for instance, Pete Loreson's CSLAM scheme. Unfortunately, we discovered earlier this year that there may be an observed resolution limit associated with the line integral-based approach in CSLAM right now, but Peter thinks that he has a method in order to fix that. And we also showed that they require a higher order treatment of upstream edges in order to maintain accuracy. This is generally true about any upstream integrated scheme. So if you have an upstream integrated scheme, you might want to run what I'm going to show you in a minute. Let me just talk briefly about what an upstream integrated scheme is. You want to flux across this edge in order to determine how much mass is flowing between these two elements. You project the velocity backwards in time to obtain a flux area. Some people just use parallelogram. CSLAM uses a arbitrary quadrilateral. And you integrate over the flux area, and that obtains the total flux that basically passes through the edge in that time. All right, so that's a very simple concept and seems to be very well grounded in physics and tends to work well. Now, the problem that we observed is when we have a very strong sheared flow, such as the Galuski test case, for instance, imposes a strongly sheared jet located in the northern hemisphere. On the cubed sphere, this is especially bad because the strongly sheared jet actually passes over the cubed sphere corners. So consequently, you're going to get a double hit of a strongly sheared jet plus very strong grid imprinting associated with that jet. So if we run a reference solution using an Eulerian finite volume scheme at high accuracy, we obtain something which looks like this using the Galuski flow field. If we use the quadrature-based flux form CSLAM, which produces the same results as the upstream integrated CSLAM scheme, we get this. Now you can see the cube sphere grid edge is right here. There's a sudden shift between some large value to the left of this cube sphere panel edge and the value to the right. And the whole field basically gets very messed up from what you would expect the converged solution to look like. It does converge eventually, but very slowly, and it's not even second order accurate, unfortunately. If we instead change the upstream integrated edge to be quadratic, that is, we use 3 sample points back here, fit a parabola through the edge, and then integrate along that edge using the same line integral approach, then we again recover the original reference solution associated with it. So that suggests that at least on the cubed sphere, if you want to run your upstream integrated semi-Lagrangian scheme, you're going to need at least quadratic accuracy in order to be able to perform well in this particular test case against corresponding Eulerian method. So a second approach that we're proposing then is using the finite volume form of the transport equation. Again, we have an evolution of an element averaged value plus a flux around the boundary. If you integrate this expression in time, you obtain a element averaged q at the next time step as a function of the element averaged q at the current time step, plus a time integrated flux through the edge, which is integrated around the boundary. So that's basically summed over every boundary. So the basic idea in this approach then is to use the Barrett and Colella type convolution that I talked about earlier, integrate the equation of motion backwards in time at time points in order to obtain, and then use a Simpson type quadrature rule in time in order to evaluate that time integral. So you need to compute 2 trajectories back for every edge center point, and then that'll give you a time integral of the f dot n term that I showed before. So that gives point fluxes at the center of every cell, or cell edge, which are normal to that edge. If we then use Barrett and Colella convolution, then we again obtain a 4th order accurate solution to the flux. And in this case, no upstream integration over areas is required. Everything is pointwise. All right, so the convolution scheme guarantees 4th order accuracy without the need to integrate over a flux volume. Monotonicity and positivity are provided using flux-corrected transport, and both approaches guarantee conservation since transport is formulated in terms of fluxes. Only 1 communication is needed per time step, very important. This will speed up your advection scheme, and both allow for a CFL of approximately 1. All right, I'm going to very quickly go through Ader finite volume methods, which is the time stepping scheme. This was discussed briefly by Matt Norman before, but I just want to discuss how it's implemented in MCore right now. So Runge-Kutta methods require multiple communications per time step. We're instead going to use local data and maintain stability and accuracy. So the most well-known one-step, one-stage scheme is the forward Euler method, but forward Euler is unstable with any spatial discretization higher than first order. And the reason for this is to some degree because the instability of the one-step forward Euler method for high-order schemes is related to its inability to take into account how spatial variation of the underlying solution affects the time integral. Notably, a first-order scheme has no spatial variation, and consequently, you can use forward Euler for it. So forward Euler approximates this integral here as delta t of normal dot flux evaluated at qn, which is the initial time. If you instead evaluate it at the midpoint, then you have a midpoint rule associated with that integral. And so the question is then, how do we obtain this q at n plus 1/2? And the way that we do that is we use local information and a Taylor series expansion. So q at n plus 1/2 is equal to qn plus half a time step times the time derivative of q. We just use the evolution equations that we know for q, plug them in there, use local derivatives that we've reconstructed under the subgrid scale in order to compute dq dt, and then plug that in there, and we get a linear evolution equation for qn at the cell center point, and then use that in order to compute fluxes. So this is effectively Hancock's scheme, which has been popular in CFD for some time. Other variations of Ader schemes are possible that bring things to higher order. So the order of accuracy is consistent with the Runge-Kutta scheme. That is, we still get fourth order convergence for many of the dynamics problems we look at. The number of communications is, or there's only one communication needed over a time step as opposed to Runge-Kutta, which requires 4 communications at least. And the maximum stable time step is about 0.8 times Runge-Kutta 4. Yeah.
Could you go through this one more time? Go back one slide.
Okay.
How are you getting fourth order with what looks to be the midpoint rule?
It's second order in time, but for the convergence studies in space, we obtain fourth order.
So it is second order.
Yes.
Imagine my relief.
So summary and future work. All right. MCore model has been developed using high-order accurate finite volume methods for accurate modeling of atmospheric flows. Variable resolution support is being developed and worked on with Chombo using centered finite volume methods. I talked about this new finite volume, semi-Lagrangian finite volume scheme that we're working on in order to alleviate some of the problems in the upstream integrated formulations of semi-Lagrangian schemes. And Ader schemes are being tested for improving performance and reducing the number of parallel communications, which, as Matthew Norman indicated earlier, is going to be a major bottleneck going forward. So this suggests a potentially significant speed up. Just some acknowledgements. Christian Jablanowski, my University of Michigan advisor, Bram Van Leer, who helped with the development of the finite volume methods, Phil Colella, who's here and is a great guy, Peter McCorkindale, Peter Loretzen from MCore, who helped with semi-Lagrangian stuff, Matt Norman, who's here, and the organizers of PDEs 2012. Thank you very much.
We have time for 1 or 2 quick questions. Go ahead, Bjorn.
Paul, how do you design your scheme for adaptive mesh refinement? As far as I understand, you use a non-conforming scheme, and this pointwise semi-Lagrangian stuff there, then you have problems to fit a parabola, don't you? Or does that take over?
So
do you lose accuracy actually? Do you lose an order of?
No, it uses Berger and Colella type adaptive mesh refinement, which is 1989. Basically, you have a high-order subgrid scale reconstruction in the coarse grid, which is used in order to fill in halo elements on the fine grid. And so the fine grid is actually run on top of the coarse grid. In order to coarsen, it's an averaging operation. So as long as your subgrid scale reconstruction is able to be fourth order accurate, then you can transfer that to the fine grid and still maintain the same order and still maintain the same accuracy.
I think we don't have time for any more questions, so we can talk to him later.